Welcome back to our YouTube channel. Today we are met by this question which states that x squared minus x minus 1 is a factor of ax to the power of 17 plus bx to the power of 16 plus 1. What is a? Now, a normal student would get the roots of this first polynomial and create two simultaneous equations with the second polynomial and maybe use Vieta's formulas, which we will learn about very soon in this channel, to simplify the two simultaneous equations. Well, I'm here to show you a much elegant, special, and very, very rare, beautiful way to answer this question. So let's get started. So first things first, let's get the two roots of the first polynomial and let's give them a symbol or variable. How about we use the Greek letter phi? I've been researching a lot of physics, and phi shows up a lot in physics. So let's let this equal the first root, which is 1 plus root 5 over 2. And let's let this, let's call it the inverse phi, equal to the second root, which is 1 minus square root 5 over 2. Now, believe it or not, these two roots have a special connection to the Fibonacci sequence. And I'll show you how right now. So, when we substitute a root into a polynomial, that polynomial gives us 0. That's what the definition of a root is. So let's equate this first polynomial to 0 because we'll substitute the roots in. Okay, so when this equals to 0 and we move negative x and negative 1 to the other side, we get that x squared is equal to x plus 1. Now let's substitute a root in. Let's use the first root. So phi squared is equal to phi plus 1. Let me just rewrite that phi squared because it looks a bit ass, I'm not gonna lie. So phi squared. Okay, let's say we want to get phi cubed. So let's say phi cubed. Now what can we equate phi cubed to? How about we equate it to phi multiplied by phi squared? Because when you multiply with the same base, the exponents add up, and there's an invisible 1 here, and 1 plus 2 equals 3. But we said that phi squared is equal to phi plus 1. So if we substitute that in, we get that phi cubed is equal to phi squared plus phi. But didn't we say phi squared is equal to phi plus 1? And if we substitute that in again, we're going to get 2 phi plus 1. So let me write that here. So phi cubed is equal to 2 phi plus 1. Now, I don't know if you guys see the connection here yet, but let's go on to phi to the power of 4. So let's equate that to phi multiplied by phi to the power of 3. What did we say phi to the power of 3 was again? It was 2 phi plus 1. So if we substitute that in and simplify, we're going to get 2 phi squared plus phi. But didn't we say phi squared was phi plus 1? So if we substitute that in, expand, and then simplify, we're going to get that phi to the power of 4 is equal to 3 phi plus 2. Now, I'm not sure if you see the sequence quite yet, but I'm not going to keep going. I'll just say ... and I will make the connection much more clear. So let's move to the small board here. Let's write the first 5 Fibonacci numbers. So we have 0, 1, 2, 3, and 5. Those are the first 5 Fibonacci numbers. Now look here. 1, 2, 2, 3. And here we have 1, 2, and 3. So let's say we want to get phi to the power of 5. That would equal 5 phi plus 3. Now let me write a general formula to make it even more clear. So if we want to get phi to the power of n, this will equal the Fibonacci number n, the nth Fibonacci number, multiplied by phi plus the previous Fibonacci number. So let's test this out with phi to the power of 4. So phi to the power of 4, n equals 4. So this is equal to the fourth Fibonacci number multiplied by phi. The fourth Fibonacci number is 3 plus the previous Fibonacci number, which is 2, which gives us 3 phi plus 2. Meaning this general formula is actually working. You can test it out with phi to the power of 5 if you want to. So let me erase all this jibber jabber now that we have a general formula. Here we go, here we go. So, what do we do now? So notice that the two roots from this first polynomial are also roots of this second polynomial. So since this first polynomial is a factor of the second one, 2 of the 17 roots from this second polynomial will be the 2 roots of this first polynomial. So if we substitute one of these roots, let's say the first one again, into this second polynomial, it will be equal to 0. By the way, this general formula also works for the inverse phi root, by the way. It works for both of them. But let's just keep using the first one so we don't confuse people. So here we're going to have that A. Actually, before I do this, let me note something that we are going to need. We are going to need 3 Fibonacci numbers. Can you guess which ones those are? I'll give you a second. We're going to need Fibonacci number 17, Fibonacci number 16, and Fibonacci number 15. So Fibonacci number 17 is 1597. Fibonacci number 16 is 987. So let me write that, 987. Fibonacci number 15 is 610. We're going to need those, and I'll show you why right now. So here we have that A multiplied by phi to the power of 17 plus B multiplied by phi to the power of 16 plus 1 is equal to 0. Now, let's use this general formula to find phi to the power of 17 and phi to the power of 16. So, phi to the power of 17 will equal, what's the 17th Fibonacci number? It's 1597. So 1597 multiplied by phi plus, what's the previous Fibonacci number? So Fibonacci number 16 is 987. So let's do 987. Now let's find phi to the power of 16. This is equal, what's the 16th Fibonacci number? 987. So this is equal to 987 phi plus 610, which is the previous Fibonacci number. So let me erase this left side because we don't need it anymore. There we go, bye-bye left side. And if you want to take a screenshot or write these two down, write them down because I'll erase them as well. Okay. So let's substitute those two into our equation here. So when we substitute those two, we're going to get that A multiplied by 1597 phi plus 987 plus B multiplied by 987 phi plus 610 plus 1 is equal to 0. Now, if we expand and group the terms here, so we expand and group terms, we're going to get that 1597A plus 987B multiplied by phi plus, let's put a bracket here, 987A plus 610B plus 1 is equal to 0. Now, remember, this also has to work to the inverse phi, which is our second root from this first polynomial. And for this to work with the inverse phi, or the second root, the coefficient of phi and the constant in this equation must both equal 0. And that's going to give us a simultaneous equation. So we're going to get that 1597A plus 987B is equal to 0. And we're also going to get that 987A plus 610B plus 1 is equal to 0. Now, let me erase. Actually, let me just write it on our small board here. I'll write our solutions on the small board here. So I'm not going to really solve the simultaneous equations like every single step. I'm just going to show you what you're going to get, like the key steps. So I'll just give you some space to take a screenshot of the two simultaneous equations if you want to. But I think that's enough time. We're going to get that B is equal to, I think it's going to be equal to negative 1,597 over 987A. Okay, and A will equal 987. Let's put a box around that. So I'm not really sure if this is a minus or a plus. I'm pretty sure it's a minus. If it's a plus, I'll edit a plus over the minus, so you'll know if it's a plus or minus. But I 100% know that A is equal to 987 after solving the simultaneous equation. And that's our answer, so we're done. Thank you for watching the video. I hope you enjoyed this very special case of the Fibonacci sequence being in a solution. Thank you for watching.